Let's start off with just one to work, to remind you of the thing that happens. Right? Inequalities involving log exponents. Right? So let's start off with one just as an exercise. How do we do this sort of thing? Right, we're trying to find the x for which this is true. For that x is the natural log of 2 minus 3x less than or equal to 1. Do you guys remember how to do it? So if you want to move over to the middle or something? Yeah, it's probably exactly the same. Yeah, Caroline, go ahead.
So e to the 1 is less than or equal to 2 minus 3x.
Okay, so be a little bit careful, because if I say something like this, say, okay, I think what you're trying to do is translate from a logarithmic statement to an exponential statement, and where, although you can do that if there's an equality, with an inequality you have to be a little bit careful. Okay, with an inequality you have to be a little bit careful. Now remember that log base b or b to the x. Remember that they preserve inequalities if b is bigger than 1, and they reverse them. Inequalities if b is less than 1. Right. So in this case, we've got log base e on the left-hand side, and so the thing to do is to take e to feed both sides into the exponential function, right? So we take x the log of 2 minus 3x, and x of 1 on this side, right? Right. We take e. Have we used this notation before? No. Okay, we haven't. What I mean is we take e of e to the this, and we take e to the this. Okay, when people write x, they mean the function. When I write x of x, I mean e to the x.
Can we just write it the second one?
Either way. But it's sort of maybe easier to understand as a function. We take x of both sides. Okay, and right, this is e to the something, right? And e is bigger than 1, and so the inequality is preserved, right? The inequality is not reversed, right? So let me put this one in brackets. It's redundant. Right? So this thing would imply this thing, right? This thing on the left here is 2 minus 3x is less than or equal to e, right? E to the x and natural log cancel each other out. And then we just solve for what x must be, right? We see that 2 minus e must be less than or equal to 3x. Dividing both sides by 3, we get that x must be greater than or equal to 2 minus e over 3. But you notice that is there anything bad about that? X must be greater than or equal to 2 minus e over 3. That's negative, right? E is bigger than 2, so we've got a negative number here, right? So really, this doesn't make any sense. All it says is that x should be greater than 0. Well, I'm sorry, let me take that down. Let's go back up to here, to our original thing. Natural log of 2 minus 3x, right, is the input. And so we know that, notice that actually 2 minus 3x has to be what? It's the input for the log, right? What's the domain of the log? Has to be greater than 0, right? Right?
Doesn't it always have to be greater than 0?
It has to be because it's the input for the log, right? Remember the log?
Always has to be positive.
The log is like this, right? It's only defined for positive numbers.
Yeah.
Right. So we see that here, 2 must be greater than 3x, right? So x must be less than 2/3. X must be less than 2/3. Okay. I'm sorry, I sort of misled you. But, okay, so what we have then is that x must be less than 2/3 and greater than or equal to 2 minus the. Sorry. So that is that's the solution.
I'm sorry, what does that say that log is
Preserves.
Like, what does that mean?
Preserves inequality and reverses the inequality. So right here, we have, so what I mean is that if you have A is less than B, then log B A is less than log B. B if B is bigger than 1, and log B A is greater than log B B if B is less than 1. That's what I mean by if you start off with an inequality and hit both sides with the log function. If the base is bigger than 1, then the inequality doesn't reverse. If the base is less than 1, then the inequality does reverse. Tiffany.
Is that the domain?
So that's the solution there. Okay.
Oh.
That's the solution. X must lie between these two numbers. Right? It must be between 2 minus e over 3 and 2 over 3.
And why did you say it would have to be greater than 0?
That was wrong. I was crazy.
Okay.
No, I wasn't thinking that. I was thinking that x was the input. I was thinking that x, we're taking log of x. If we were taking log of x, then x would have to be bigger than 0. Right? But we're taking log of 2 minus 3x. Right? If x is a big negative number, then we're taking, that's fine. Right? We're taking log of a positive number. Right? X can be negative. There's nothing wrong. Okay. What we need is for this thing, we need this thing to be, we need 2 minus 3x to be positive. We don't need x to be positive.
So when you make it equal to 0, that finds the domain? No. What happens when you set it equal to 0?
When I said
What
when I said 1 equals 0.
When you set your 2 minus 3x. Or not equal to 0, but greater than 0. What does that find for it?
So that is just saying that we have this extra condition, right? The domain of the log, right? The domain of the log is that is from here onwards, right? Is from 0 onwards, right? So you can't feed the log a negative number.
Yeah.
Right? If I say, what's log of -1? The answer is, there is no such thing. Okay. So we need this 2 minus 3x to be bigger than 0. Otherwise, we're not going to get anything sensible. Okay. So we worked through this thing, and we saw that x had to be bigger than 2 minus e over 3. But we also have to require that log of 2 minus 3x makes sense. In other words, that 2 minus 3x has to be bigger than 0. Right? And that gave us that x has to be smaller than 2/3.
Okay.
Right? Because if we just stop here and we say, oh look, x just needs to be bigger than 2 minus e over 3. So if I take x equals 10, this will work. And then I try x equals 10 into here. Right?
Mm-hmm.
And I say, oh look, let's see, log of 2 minus 30, log of -28 is less than or equal to 1. Is that right? No, that's not right. Right? So we have to make sure that our domain that our x, that we're still lying in that domain. This makes sense. Okay. Okay, any questions about this one? Okay, I'll say it again. So we started off with this logarithmic inequality. Okay, started off with the logarithmic inequality, and then we exponentiated both sides. Right? We exponentiated both sides. Exponentiation preserved the inequality, and we ended with this inequality. And then we said, okay, so x must be greater than or equal to this. But we also need this thing to be greater than or equal to 0. So we saw that that happens when x is less than 2 things. And so together, we get the range of our solution. So,
just to make sure I understand it, so with an inequality, you can never be like, e to the 1 is greater than or equal to 2 minus 3x. You can never translate it like that. You just have to like do the log on both sides or something.
you can, but as long as you keep in mind that if what happens if you use a different base, if the base is less than 1 or the base is greater than 2. Okay. So I mean, if you understand what you're doing, yes.
Okay.
Right. Right. If as long as you remember that that the translation will be that the sign will reverse if you do it with a base that's less than 1. Okay. So yeah, it's fine to do that. It's fine. It's equivalent. But just be careful.
So that would change to e to the 1 is less than or equal to 2 minus 3x, or the other way?
Greater than equal to. Greater than equal to. Because the base is bigger than 1. Base is bigger than 1. So somebody's saying, isn't there some shorter way of thinking about this, right? And the answer is yes. Sort of an abbreviated way is to think that, well, it's true that this is equivalent to e to the 1 is bigger than or equal to 2 minus 3x. But I really prefer it if you thought about it this way, because this is sort of like, I don't want to think about what actually happens. I prefer if you, it's true you can do it this way, but I think it's more, it sort of makes more sense to do it this way. This is the way that will lead you to more things. Right. Let me. So the function f of x equals negative x. If we look at the function f of x equals negative x, that's this function here, right? Just for an aside, right? Here's the function f of x equals negative x. Right? And you notice that if a is less than b, if a and q is b, what can you say about f of a and f of b? Well, f of a is here, f of b is here. F of a is bigger than f of b. Right? This function is a function that reverses the inequalities. Right? As you know from elementary school, right? If you have 2 is less than 3, and if you put both sides into the minus function, then you have to switch the sign. Right? Why? Because this function is a decreasing function. Right? If you have a is less than b, f of a is less than b, f of a is bigger than f of b. Okay. If your function is decreasing, it will reverse the sign. If your function is increasing, it preserves the sign. That's what's going on here, right? Increasing functions preserve inequalities. Decreasing functions reverse inequalities. Right? This was really mysterious to me as a kid, right? Wait, why would you, if you multiply both sides by a negative, then you have to reverse the sign? I mean, it seems that it works. But why is, well, if you think about it graphically, it's pretty clear. And so, you know, coming back to here, the log again, we said this on Friday, but you have this log function, right? But it's easy to see, it's easy for me to draw with the exponential function, because b of the x would be bigger than 1, because b of the x would be less than 1. Right? B of the x, if b is bigger than 1 is an increasing function, if b is less than 1 it's a decreasing function. So these guys preserve the inequalities, and these guys make. These guys preserve the inequalities, and these guys, you know, reverse the inequalities. That's what's going. That's really what's going on.
Wouldn't the one you drew down there? That's reversed, right?
That's right. That's right. That will reverse it. So if I have A, B, then B of A will be bigger than, right? Even though A is less than B, B of A is bigger than B of B. Right? The inequality gets reversed.
Well, isn't that just common sense? Because it would be like -1 is less than 2.
Yes, it is common sense.
Yeah. So why is this important? I mean, I don't mean it.
Well, let me say it this way. Is it obvious that if I took log base a half of this, then I have to reverse the inequality?
Oh, no. Okay.
Yes, it is.
Well, yeah, no, it is, but without that, it wouldn't be.
Yeah.
Okay.
It is obvious now that you know what it means.
Yeah.
Right? The log of a half, log base half, is a decreasing function, so you reverse the inequality.
Okay. Just throwing a spark in class.
No, it's good. It's good. It's good. Right? Actually, that's how it should be. That's how it should be. And you might be like, well, I don't believe that. Well, what?
I can see you in class being like, I don't believe you.
It's okay. The trouble with math class is that actually everything in math can be defended. And so you start thinking like, oh yeah, everything that the teacher says is right for some, just for some strange reason. Like the teacher is always right. Whereas in other classes, everything is open to debate. Right? If you in core, whatever the teacher says, that's open to interpretation and debate. And actually, the way you want to think about the math class is more like that. I think everything actually should be open to debate, and watch the teacher try to wriggle his way out of and explain exactly why it is so. It's actually really dangerous to be a math teacher because you start to believe that what you say is true.
Does that happen to you in your higher math classes when they ask you stuff and you can't answer it? Or?
Sometimes it happens. Yeah, sometimes it happens. But even in those classes, it's sort of the same thing. As long as I have thought about it beforehand, then it should be that I can explain everything. But as I said, it's sort of a dangerous state for any human being.
The last math teacher said the thing, right?
Oh, yeah.
It's dangerous to be a math teacher.
Sure is.
I never thought I'd hear somebody say that.
Yeah, it's very dangerous. Just as a human being, I think it's a bad thing. Okay, let's go on. So let's go on. Something more. The best part is when students, sort of rationally challenge you, and you're forced to make things clearer and clearer. I had a student who stayed after class. So about 4 or 5 years ago, I had a student who stayed after class to argue with me for about 40 minutes about a particular limit. The limit of sine 1 over x as x approaches 0, say on the right-hand side, didn't exist. So you have this function, the sine function, but you composed it with the 1 over x function. And it goes like this, and it starts speeding up. It's just going, it goes crazy as it approaches 0. And so it doesn't approach any fixed value. And I said, oh, this thing doesn't exist for such and such a reason. And she stayed with me to argue about it for about 40 minutes. That was actually like a high point of my life at the time.
Did he win?
Maybe. But yeah, I still refer to, like, when people say, what was your favorite moment? You know, like you get interviewed for like college, and they say, what was your favorite moment in teaching a math class? Or tell us about a favorite moment, and I often refer to this. Okay. Okay, a more complicated example. Same thing, harder. Log base 2, 2x minus 1, x minus 2 is less than 0. So I'll show you guys how to do this one. Right. Well, no, maybe you guys tell me from the beginning. What would you do? You got log of something is less than 0. Again, you take 2, right? You take 2, feed this thing into the 2 to the x function, right? So feed the inequality into the 2 to the x function, right? You got this a is less than b, and you feed it into this guy. Well, it's going to be this is less than 2 to the 0, right? 2 to this is less than 2 to the 0, right? And 2 to this is, of course, just the argument here, right? Because 2 to the x and log base 2 cancel each other out. No, question? Yeah? Okay.
Isn't 2 to 0 just 1?
Yes, it is 1. It's not just 1, but it is 1.
It's 1.
It is 1. Okay. So, okay. And then the other thing we have to keep in mind is that this thing has to be, I mean, maybe we can do this later, but, you know, eventually I'm going to say, you know what I'm going to say. What I'm going to say about this. This thing must be greater than 0. Right? So secretly, you keep that in mind. It's going to be greater than 0. Okay. Okay. So we're looking for where this is less than 1 and greater than 0, and how do you do it? Okay. Okay. So let's think of this in pieces. Okay. Let's do this first piece. 2x minus 1 over x minus 2 must be greater than 0. Okay. This you actually know how to solve. Right. This is a rational function. It's a rational function. This is an inequality involving a rational function. You remember how to do it? Right. You find out where this guy equals 0. Right. Where the guy has poles. Right. You test points in between. You forgot. No bells are going on. No lights are going on. Right.
Is this when you find for like the x and y?
No, well, remember how it is, right? You look where the top is 0, right? Where's the top 0? So where is 2x, this thing equal to 0, right? Well, that's at 2x equals 1, so x equals to half. Right, so here, 0, 1, equals half. Right? You know that it crosses at here, right? And also at 2, we have a vertical asymptote. Right? We've got a rational function. Where is it positive? Well, we just need to test points in between.
And we knew the vertical asymptote was because it was x minus 0, then it's x equals 0.
Mm-hmm. Right? This is your old knowledge. Okay, and then we just test in between, right? Well, at 0, right, on the left-hand side here, let's test at 0. We get -1 over -2 is positive. Okay, so in this range it's positive. Right. Between 1 and 2, let's test at 1, say. Right. At 1, we get 2 minus 1, that's 1. 1 minus 2, that's -1. So we get a negative number, so it's negative here. Right. And then over here, we choose some gigantic number, and we see it's positive. Okay. So this inequality, the inequality is satisfied in what? Sorry.
Inequality is satisfied in
Where?
between, is 0 or whatever value you took.
This is 1/2. Sorry.
Oh, half.
This is a half, this is 2. Okay, so we're positive between negative infinity and a half.
And half, and then, is that 2?
That's a 2?
Yeah, 2
Very good. Right, so between negative a half and, I'm sorry, negative infinity and a half, and between 2 and positive infinity, this thing is okay. Okay. This part, you should be nodding your heads because you've seen it before. Good. Good. Okay, now let's do the second part. Right, 2x minus 1 over x minus 2. X minus 2 must be less than 1. Okay. We're going to play the same game. We're going to play the same game. To do so, we'll just switch it a little bit. Let me move the 1 to the left-hand side. Look.
Why wouldn't you just multiply both sides by x minus 2 and have 2x minus 1 be less than x minus 2?
Well,
And
you
then
could,
solve it.
but you have to be careful that you have to break it into 2 cases, right? When x minus 2 is positive and when x minus 2 is negative, right? Because when you multiply both sides, if this were negative, and you multiply both sides by it, then the sign switches.
Yeah.
So you can do
So you
it.
have to assume that x could be positive.
You have to do, you can do it, you have to break it into 2 cases. You say 2x minus 1 is less than x minus 2, assuming x minus 2 is positive, right? And then assuming x minus 2 is negative, then you have 2x minus 1 is greater than x minus 2. And you could do it that way. That's fine. I'm gonna do it in a way that's similar to the previous way. Okay, but similarly that'll work. It's perfectly fine. Okay. So I'm gonna do the rational functions way again. So I made the 1 look like this, and I moved it to the left side. Okay, this is 1. Okay. And so I get 2x, so I get x plus 1 over x minus 2 is less than 0. Sorry?
You just simply shifted the 1 to the other side?
Yeah. So, right, you're allowed, with an inequality, you're allowed to add the same, subtract the same thing from both sides.
Okay.
So I subtracted 1 from the right, and I subtracted 1. This is 1 from the left. Okay. And then I'm using, fraction, arithmetic to combine these terms together. Right. And now we play the same game as before, right? We've got here 0, negative 1, positive 2. At negative 1, we cross the axis. Right? At 2, we have an asymptote. At 2, we have an asymptote. Right? And then we play the same game. We're trying to find where this thing is less than 0. So we plug in some values. I'm going to plug in, say, negative 1,000,000. Right? And I get something very negative over something very negative. That's positive. So we fail the inequality here. If I plug in 0 here, I get 1 over negative 2. It's negative, so it's good. And then I put in some gigantic positive number, and I get something positive. Okay. So the only place that this is satisfying, so this inequality is satisfied in negative 1 on 2.
Would it be negative infinity?
No, because we're looking for where the thing was negative.
Oh, so I'm looking for where the sign is negative.
Yeah, right. Where the thing is negative, well, the sign is negative between here and here. Okay. For this inequality, x must be between negative 1 and 2. For that inequality, you must be between negative 50 and a half and 250.
So for that one, we were searching which one was positive,
Yeah,
and then here we're talking about where x has to be negative.
yeah, yeah. Because our inequality turned into this thing, right? We're looking for where this function is negative. Over here, we have a different function, and we're looking for where that function was positive. Right? But we've got two pieces. Remember where those things came from, right? Our input has to be between 1 and 0. There's a place where it's bigger than 0, and a place where it's, we want it to be bigger than 0 and less than 1. You learn.
So when you get an equation, you want to immediately set both parts of it as greater than or less than 0. Is that like the rule of thumb?
Oh, you're saying why do we make it 0?
No, well, I mean, I get why, but like, is that the way to do it every time? You just want to make it, set it equal to 0 so you can solve the way we're solving it?
That will, if you set it, if you, so the technique we had earlier was basically, where is a rational function bigger than or equal to 0? Right? Comparing the rational function to 0. So if you want to use that, then we have to make it look like, that.
And you do that for both, like, sides?
Yeah, we did it for both sides.
Okay.
Yeah. So this is problem 61. As you see, it's a high number problem. Maybe one of the harder problems in this section.
You made it seem quite easy though.
Okay, good. Okay, so the last thing is, right, so we want both of these things to happen, right? Both of these things to happen, and so where are both of them true? This one is true here, that one is true there. Where are both of them true?
Negative 1 to a half.
Negative 1 to a half, that's right. Between negative 1 and a half, right? Because this one is true from negative infinity to a half, 2 onwards, right? Negative infinity to a half, and from 2 onwards. And that one is true from negative 1 to 2, right? So between, let me draw sort of floating negative 1 to 2. So where are they both true? Well, it's going to be in this intersection here, negative 1 to a half. Right. So this happens, which is true for x exactly in negative 1 from a half. In the intersection, right? The intersection of those solution sets. Those two solution sets that we just got. We saw one equation, one inequality, we got one set. We saw the other inequality, we got another set. Where they're both true, well, has to lie in both solution sets simultaneously.
Would it be true if you said 2x minus 3 and then over x minus 2? Would this solution set for that be negative 3 over 2?
No, that's a simple.
Okay, I just wanted to see if there's a correlation.
Sorry, no.
No.
Always looking for some quick way out, right?
No, I was just looking.
No. So no, not so. At least not so. Yeah, not so straightforward. Okay. Looking for the easy way out is actually a hallmark of. It's actually what we do all the time. So it's nothing. I shouldn't tease you. Okay. Yeah, like if you found some quick way out that always worked, then that would be incredible. Okay. Okay. Well, there's no need to rush. So, okay. So do you want to do another example of this? We have another example. Would that be, you guys want to okay, good. Okay, so same sort of thing. So here's problem 9. This would be easier. Log base 10 of x plus log base 10 of x minus 2 is less than or equal to log base 10 of 24. Okay, so this is sort of along the same lines, but easier. Actually, this one's easier than the last one, but it still has some of the same ideas. So I'll let you try it. 10 minutes left. Just take it easy. Sure, yeah. You want to try it?
You can combine the two.
So it becomes log base 10x times x minus.
Right. Because the sum of logs is the log of the product, right? So we get this.
And then you can, since they're the same, you can equal them. So it's like x and x minus 3 is less than or equal to 24.
Okay, so just now you said because it's the same thing, you can just get rid of the logs. That's a little bit risky because you can if this were like a half, then and you just erase logs on both sides, it would be wrong. Okay. Right. So right, the way you want to think about it, remember, is that we're going to take we have this inequality and we're going to feed it into the 10 to the x function. Okay. It's not that we just erase the logs. Okay. But we cancel them off by feeding both sides. Feed the inequality into 10 to the x, the function 10 to the x. And the 10 to the x says, I preserve inequalities. Okay. And so it says, okay, I'm going to give you back. The 10 to the x guy is going to cancel off the logs, right? And preserve the inequality. Okay. Yeah, and then?
Becomes x squared minus 2x minus 24 plus 0. And I just got up to there, so you can use the quadratic.
Use the quadratic formula. I mean, this one backwards, right? And this one backwards into x minus 6 plus 4. So,
Question,
Yeah.
can you, coming back to the second step, can you just take log to the other side? So it would be log, and if you were to expand that, x squared minus 2x minus log 24 is less than or equal to 0.
so you say, well, log x squared minus 2x minus log 24 is less than or equal to 0.
And then you would use log rule, so you would divide x squared. So it would be log base 10, x squared minus 2x divided by 24. And then you take 10 to the other side, so it would be 10 to the power 0, which is equal to 1. So you get x squared minus 2x by 24 is less than or equal to 1. Or is that wrong?
No, that's fine. That's fine. That's fine.
Oh.
So you get log base 10. It's perfect. That's how here. And divided by 24 is equal to 0, right? And then you take 10 to the, you feed both sides into the 10 to the x function. You get this, where 24 is less than or equal to 10 to the 0, which is 1.
So this is.
And then you get the
But
same.
it's right to do that.
It's perfectly, it's fine.
Okay.
Yeah, that'll be another,
Yeah.
and perfectly, you ended up the same place.
Okay.
As long as you end up As long as you do correct things and are heading in the right direction, you'll have those.
Okay. I'm confused how I know you say like feed inequality into 10x, but I don't understand where the log 10 went.
Remember, so when we do it, you take this thing, a less than equal to b, and you have 10 to the a is less than equal to 10 to the b. Right? 10 to the a is less than equal to 10 to the, oops, not 10, 10 to the b, right? And then you remember that 10 to the log base 10 of
Okay.
something is just that something. Right? 10 to the log base 10 to 24 is just 24.
So whenever you have a log base of whatever, and it's the same on both sides, you can just do that.
Yeah. You could just skip to here. As long as you remember, what the function does to the inequality. Right? We're taking 10 to the block, so we have to preserve the inequality.
So it doesn't always have to be 10. It can be like,
It could be 5, or it could be a half, but if it was a half, then you have to flip the sign.
yeah.
That's the only thing. Okay, so our question is, where is this less than or equal to 0? Where is this less than or equal to 0? What do we do? Carol?
So then you just do x minus 6 less than 0 and x plus 4 is less than or equal to 0 and so on.
No. So I think you're thinking about if it's equal to x minus 6, x plus 4 equal to 0. That's true that this is the same thing as saying gotta be one of these things. But it's not true for inequalities.
Okay.
It's true that if you have a times b equals 0, then one of these things has to be 0.
Got it.
Right? If a and b is less than or equal to 0,
No
it's
one.
not true that
Right.
that-
Okay.
it's not true that a has to go up to
Okay.
so we just do this in the way that we did before, right? Where are the zeros of this? Well, at 6, we have a 0, and at maybe 4, we have a 0. And then we test points in between. Right? So we take a gigantic negative number, we get something positive. We take a 0, we get something negative. Right? We take a gigantic positive number, we get something positive. So we see that this is satisfied where? Can somebody read it off for me? Where is it satisfied? Alex?
Between negative 4 and 6.
Negative 4 and 6 inclusive or including those points or not inclusive?
Including this one?
Including those points. Because the function is
Yeah.
0 there, and we're checking where it's, this thing is less than or equal to 0. So that seems to be the solution. That seems to be the solution, except we have to check, we have to say, look, let's look at back at our original thing. What constraints do we have on it? Well, x has to be,
So it can't be negative.
right? X has to be bigger than 0. Also, x minus 2 has to be bigger than 0.
So it's just 6.
Well, no. So we have to be, x has to be bigger than 0, right? We have to be on the right side here. And x has to be bigger than 2 also. And so I'm going to put 2 here. And we have to be here. We have to be on the right side of 2. So what's our solution set then?
2 to 6.
2 to 6 inclusive on 2 or exclusive? Exclusive, right? So between 2 and 6 is inclusive, is the actual solution.